The first big idea on the AP Computer Science Principles exam is creative development. The topics in this category are going to be about 10 to 13% of the questions on the multiple choice exam, but even though that's a small number of the questions, this big idea provides an overarching framework for why you learn the specific skills and practices you will with the other big ideas. The creative development big idea asks, what is the most effective way to complete and refine a computing project? What's the best strategy to take to make some sort of program or piece of hardware or software that could be revolutionary and change the way society, economy, or culture might work? Before we dive into things, we need to kind of set some standards for definitions and what terms mean when we use them in the context of computer science. The first term that you'll see a lot is computing innovation. A computing innovation is a very vague thing. It's the hardware or software that rely on code that can be used to solve problems or extend creative expressions. What this means is it could be a physical device, like a gaming console or a self-driving car with sensors, or it could just be a program, like some current AI programs that could write songs or poetry based on minimal inputs. These programs will have some sort of purpose, but they don't need to necessarily be strictly utilitarian. There are ones that do solve actual mathematical or scientific problems, but programs that allow you to create art or music would also fall under a computing innovation. If you plan to make a computing innovation, you have to start with a purpose, with a goal, because without that, you have nothing you're working towards. As a developer, if you have a clearly defined goal, not only will it help you develop the project, but it'll help you use that code and use that program once you have it done. If you're struggling with this, one of the best sources for information is going to be your audience. It's going to be who will use the program or hardware or whatever computing innovation you make, and how can you best meet their needs. When we say a program, what it means specifically is just a collection of code. Programs live in the software world. It's not something tangible. It's something that we would run on a piece of hardware. When we describe programs, we have a couple of options. We could describe the general purpose, like it's just a calculator, it's just a game, or we can give specific details about how the code runs, maybe specifics about how exactly it manipulates data or makes calculations. When we talk about a program's behavior, this is the specifics of what it does as it runs, how the user interacts with it, what it does with the inputs, what outputs it generates live as they're using your program. And sometimes we'll refer to just specific code segments within a program instead of trying to tackle the thousands or tens of thousands of lines of code that are in a full-scale computer program. The inputs of a program are the data that gets sent into the computer. It could be things like putting your age when you log in for a website, or it could be things from sensors, maybe things like temperature or water level or the weather. The outputs are what the program then sends back. It might send it directly to the user, or it could send these outputs to other computers to do further calculations. It creates these outputs based on the inputs it's provided, or maybe some hard-coded internal values, things that were already part of the program, and it's just been commanded to send that information out. These inputs and outputs, again, are a variety of sources: text, video, audio, tactile sources, so things like physical feedback, haptic feedback. Anything that goes in and out of the program will count as inputs and outputs. There's another category of phenomena called events. Events are things like clicks and key presses, and these are important because they could change the sequence in which a program runs. Maybe a program will run in a straight sequence until someone hits a button to either stop it or send it to a new line of code. Event-driven programming is based around this idea, where it waits for things like button presses or input fields to be changed to make something happen. The design process could happen a couple of different ways. It could be a rigorously structured form. It could be something where, especially if you're working with a team, you have a set starting point where you're investigating ideas, a set design phase, a set prototyping and testing phase, and this is all very rigorously structured. But can also be something more exploratory. It could be something a little more adaptable, where you just kind of go with the flow of things and adapt to whatever new information comes in and change the program as needed based on feedback or internal testing. What's important regardless of the strategy is that there's an incremental process, that you're not trying to write an entire program at once, but you're approaching each question one at a time, addressing each little piece before you add it to this whole massive computer program. The investigation phase is essential in order to figure out what your limits are when making your program and what the potential audience of your program might want to see. What needs need to be met in order for your program to be successful. You can get information via investigation through a couple ways. You can do surveys, interviews, tests, or just observe the world around you and see what problems need to be solved. As you said about designing your program, again, this can be approached with a myriad of ways. You could brainstorm, you could storyboard, or you could dive into the more technical components and just start listing out what functions you think your overall program is going to need. The most important thing, though, is that as you write your program, you maintain documentation. Program documentation is just a written description of either the functionality of the code, or an event, a procedure, or program. Maybe it's explaining exactly how it works, maybe it's a general overview of what a certain function might do, or it could be how it was developed, or just an acknowledgement to the author of that segment of code. As you're coding, you can do documentation via comments. These are lines written directly in the program code that might explain the functionality of a method, define what a variable stands for, or again, just attribute the work of a developer for a certain segment of code. Documentation should be an active process. It should be something that you do as the code is being written, not something you go back and do after the fact. As you're writing code, you're inevitably going to run into errors. There's different types of errors, and being able to articulate what type of error you're encountering is important to being able to solve it. A logic error is when there's a mistake in your actual algorithm, a mistake in the process that you've asked the code to run. This will lead to the code behaving incorrectly or unexpectedly, but that's based on your expectations. The code is going to do exactly what it says. It's an error because it's not doing what you think it should do. A syntax error is usually caused by a typo or not understanding what the language's structure is. Things like missing punctuation, misspelled words, or incorrect capitalization. Runtime errors are mistakes that happen as the code is running, and overflow errors happen when dealing with numbers that might be larger than a computer's memory can handle. It might have only put aside a set number of bits to accommodate a value, and if you put a number larger than those bits can represent, you'll run into an overflow error. To address these errors, you have to approach it with different debugging strategies. You could be using test cases, debugging programs, visualizations, where there's things that might run through your code line by line, or adding additional output statements to try to figure out where in your code something's gone wrong. Being deliberate about choosing your test case inputs is important to solve these problems effectively. The best way to do this is to understand the scope and limitation of your program, so that you can choose values from maybe the extremes and the middles of that range and find out where something's going wrong in your code. This whole process has been made easier in our modern day thanks to new technology that lets you better collaborate with other people, whether it's people you know on a direct team or just strangers out on the internet who can help answer questions for you. There's better connections not only between your team, but with your potential audience as well, allowing you to get useful feedback to refine your program. Now, to collaborate, it's going to require some strong interpersonal skills. You need to be able to effectively communicate your ideas, be able to effectively communicate what's going on in your code, and you need a strategy for conflict resolution. You might not always agree with other people on your team as to what your program should do, and you need to have a strategy for how you'll address that and the compromises you'll make. The collaboration is essential to making a successful, positive product. It lets you have a wider team, which means there's a wider amount of perspectives and views that go into your product, which help reduce the bias and any problems it might unintentionally cause.